welcome to the fourth lecture of fifth module of this course called Game Theory in Economics. Before we start this lecture, let me take you through what we have been discussing so far. We have been discussing extensive games. Extensive games are those games where the actions are taken step by step, not simultaneously. So, at one stage some particular player might be taking some action from a set of actions, and in the next stage some other player might be taking his or her action, and that is how the game progresses. And it may happen that a player who took an action in stage 1 might be taking some action in stage 4 or stage 15, so it does not matter. There could be repetition of the same player in different stages. So, this is the general setting of a strategic extensive game, and we have been discussing not extensive game in general, but extensive game with perfect information, where every player knows the actions of the other players which have been taken before his action is required to be taken. We have also defined Nash equilibrium in an extensive game. We have said that in a Nash equilibrium in an extensive game, it must be the case that, like in the case of strategic game, the strategy of every player adopts in that Nash equilibrium should be such that if any player deviates from the strategy in the equilibrium, her payoff will not go up, and if her payoff does not go up, then there is no reason why any player should change his or her strategy from the Nash equilibrium strategy. So, this was the general definition. We shall do what we shall do today is to just check how we have understood the idea of Nash equilibrium by solving one problem, and then we shall try to go beyond Nash equilibrium. So, this is one exercise of finding Nash equilibrium. Let me draw the game first. So, this is the game tree as we call them. You can see that here player 1 moves in 2 stages. In the first stage, player 1 gets to move and he can take action C or D. If he takes the action D, the game ends there, where he gets 2 and player 2 gets 0. If he takes the action C, then it is now player 2's turn to move, who can either take the action E, in which case the game progresses further again to player 1. But if player 2 takes the action F, then the game again ends, and in which case player 1 will get 3, player 2 will get 1. And if E is taken by player 2, then player 1 gets to move in stage 3, and the actions that he can choose from are G and H. If G is chosen, then he gets 1, player 2 gets 2. If H is chosen, both of them get 0 each. Now, suppose we want to find out what is the or what are the Nash equilibria in this game. So, how shall we go about finding the Nash equilibria? First, I shall try to find out the strategy set, the set of strategies of player 1. Here the strategy set of player 1 is the following. This is the strategy set of player 1. They are the strategy set consists of 4 strategies. CG, which means that in the first stage, when the history is empty, he will take the action C, and the meaning of G is that if the history is CE, then he will take the action G. So that is the meaning of CG. Likewise, there is CH. So at first stage he is taking the action C, and in the last stage he is taking the action H. And there is DG and DH, which means that which has a problem of interpretation, as we have seen before. What it means is that in the first stage, when the history is empty, player 1 is going to take the action D, and he is specifying that in case the history is CE, which is evidently ruled out by his own action D, nevertheless, if the history is CE, then the action that he is going to take is G. So that is the interpretation of DG. Likewise, DH. So these are the 4 strategies of player 1. And what about player 2? His strategy set consists of only 2 elements. He gets to move after the history C. So either he can take the action E, which is one strategy of his, or he can take the action F, which could be the other strategy. After we have written down the strategy set of each player, the next step is to find the strategic form of this extensive game. That is, we look at this game as just like a strategic game, and if it is a strategic game, we can find out the Nash equilibrium by drawing the payoff matrix. So I write the strategies as actions, and once I have written them down, I can write the payoffs also. If I combine CG with E, the payoff is 1, 2. CG with F, basically the game is coming from this node to this node and going to this terminal history. So this is 3, 1. CH E is 0, 0. CHF is again 3, 1. If the strategy of player 1 consists of the action D, obviously the game is ending in this 2, 0 itself, this terminal node itself. So all this payoff for this strategy profiles will be 2, 0. And looking at it, if I have to find out the Nash equilibria from this strategic form, then I know how to find it. I have to look at the possible deviations from any action profile, and we have to see if those deviations are profitable or not. If they are not, then we have a Nash equilibrium. So by doing that, I can see that this is a Nash equilibrium, this is one, and this is another. So Nash equilibria are the following: CHF DGE DHE. And what is the justification for this Nash equilibria? How we are certain that they are Nash equilibria? Well, we have to look at the deviations, and if the deviations are not profitable, then they are not Nash equilibrium. For example, let us take this strategy profile DGE, D, G and E. Now, why is this a Nash equilibrium? If player 1 is playing D and G, then from player 2's point of view, if he deviates, how can he deviate? He can deviate by playing F instead of playing E. But by deviating and by playing F, he is not improving his payoff, because the payoff is remaining at 2-0. So, deviation is in this case not profitable. Therefore, from player 2's point of view, he is doing the optimal thing. From player 1's point of view, there could be two sorts of deviations. One could be after the empty history. Here, if he deviates and chooses C instead of D, then given the other actions specified by this strategy profile, we shall reach this terminal history C, E, G, and therefore he will get 1. 1 is less than 2. Therefore, there is no point for 1 to deviate as far as the action after empty history is concerned. What about this action G? Well, if he changes his action and takes up the profile, takes up the strategy DH instead of DG, then his payoff is not improving, because the payoff remains at 2. So, it does not matter if he changes this action from G to H, and thus changing the strategy of his payoff remains at 2-0 at 2. So, we can talk about other sorts of deviation of player 1 also. He can deviate to CH, for example, but CH is unprofitable because in that case he will get 0, whereas now he is getting 2. So, this is a Nash equilibrium strategy profile. Likewise, these two can also be shown to be Nash equilibrium. So, this was the definition and application of Nash equilibrium in extensive game. But we have also seen in the previous lecture that the idea of Nash equilibrium in case of extensive game is a little problematic. Problematic in the sense that it is not robust, it is not a very robust concept, because there might be Nash equilibria where if a player deviates from the strategy that is specified in the Nash equilibrium strategy profile, then those deviations will generate a non-optimal action or non-optimal strategies on the other players. So, this is something which we have seen before in the last class. So, this was the familiar entry game. So this was the game. There were two players. One is the incumbent, maybe the monopolist firm in the industry, and there is a possible challenger, a new entrant, possible new entrant, who will be called the challenger. And if the challenger stays out, then it is best for the incumbent. He gets 2, the challenger gets 1. If the challenger gets in, then the incumbent might like to fight with the challenger, in which case it is worst for both of them, they could get 0 each. Or the incumbent can choose to accommodate, in which case the incumbent gets 1 because he is no longer the monopolist, challenger gets 2. In this setting, what we have seen that there were 2 Nash equilibria. I am just repeating the conclusions that we have drawn in the last lecture, so that we can link up to the discussion of this lecture. One was in and accommodate, the other was out and fight. There were no problem as far as in and accommodate is concerned, but what we have seen is that there was a problem as far as out and fight is concerned. Out and fight is a Nash equilibrium, there is no doubt about it, because given that the challenger is choosing out, the incumbent can choose either fight or accommodate. It won't make a difference to his payoff, which remains at 2. So fight is absolutely okay. From the point of view of the challenger also, as long as the incumbent is choosing fight, the challenger is better off by choosing out, because if he gets in, there will be a fight, in which case the challenger will get 0. So it is better for him to choose out and get 1. However, there was a problem of interpretation with this equilibrium. The interpretation problem was the following, that in Nash equilibrium, the idea that we are invoking is the idea of a steady state, which means that I have been observing the behavior of the other players, and by observing the behavior of the other players, I form a belief what their actions will be when I get to play with them, and those beliefs are proven to be true when we actually play the game, and that is how the game progresses. But here, when the game is structured in a sequential way, it is an extensive game. Outfight is a strategy profile where the challenger never gets to see the action of the incumbent, because he is staying out, because the challenger is staying out. So though the incumbent is telling him, I will fight with you, that action of the incumbent is never observed if the challenger stays out. And if there is no experience as far as the challenger is concerned, he cannot form a belief, a credible belief regarding the action of the incumbent. So there is this problem of interpretation, that you cannot see the action of other players, where those actions are included in the strategy profile. And one way to rescue the Nash equilibrium concept in such a dilemma is to say that, okay, I know that out and fight is the equilibrium and the challenger will choose out, but it may happen that from time to time the challenger does some experiments. He sometimes chooses to go in. So in those cases, when he does the experiments, the incumbent chooses fight. So these are observations, these are real life observations. So there are cases where the challenger gets in and the incumbent has fought with him, Therefore, the challenger or the player who is in the place of the challenger forms the belief that if he gets in, the incumbent will fight with him. That is the strategy of the incumbent, right? The strategy of incumbent is fight, which means that if you get in, I will fight with you, and which the challenger gets to see by experimenting from time to time. So, that could be one way of rescuing the idea of Nash equilibrium in extensive games. But in this case, that path, that way out is not open to us. Why? Because if the challenger indeed gets in by experimentation or whatever, maybe by error also, the incumbent will find it suboptimal to fight with him, because if he fights, he gets 0, whereas if the incumbent accommodates, he gets 1, which is more than 0. So, even if we try to interpret this Nash equilibrium where the players can do some experiments, can make some errors and reach to the actions, takes the actions which are not the equilibrium actions, then the action specified by the other player is not optimal, which means that this idea itself, that this is Nash equilibrium, all right, but this idea, this Nash equilibrium itself is not a robust equilibrium, it is not a robust steady state, because if some player deviates, then the action of the other player, which is specified by this Nash equilibrium profile, is not optimal. That is why it is not a robust steady state. All right. So, we have to have a more robust, more reasonable concept of equilibrium if we have to deal with extensive games with perfect information. A notion of equilibrium, a notion of steady state, which is more reasonable, more logical, and more the term that I have just used, robust, than the idea of simple Nash equilibrium. So, the idea that we shall develop now is what is known as subgame perfect Nash equilibrium. To define this new concept of equilibrium, which is a little bit more than the idea of Nash equilibrium, let us first define what is a subgame. So, we have to define what is a subgame of a game, and once we have defined what is the subgame of a game, then we have prepared the ground to define what is a subgame perfect Nash equilibrium. So, let me go to the definition. This is the definition. Let gamma be an extensive game with perfect information with player function P. So, if you remember, P is a player function which is applied over non-terminal histories, and if I apply P over H is a non-terminal history, then it gives me the identity of the player whose turn it is now to move, to take an action. For any non-terminal history H of gamma, the subgame gamma H following the history H is the following extensive game. So, suppose there is a sub-history or what is known as a non-terminal history H of gamma, then corresponding to this non-terminal history H, there is a subgame which we shall call as gamma H, and it is defined as the following. Now, this gamma h itself is an extensive game, so it has to have 4 elements which we have to specify. The first is the player set. So, this is element number 1. The players in this gamma h is the players is the set of players in the original game, that is the original game gamma. Second element that has to be specified is the set of terminal histories. So, how are the terminal histories of gamma h defined? The set of all sequences h dashed, this h dashed, the notation has not come really properly. So, how is it defined, the set of terminal histories? The set of all sequences h prime of actions such that h prime is a terminal history. So, h is a non-terminal history of the original game gamma. From h, if there are maybe n number of sequences of actions h prime such that h prime is a valid terminal history, then every such h prime will be a terminal history in the subgame gamma h. Thirdly, I have to specify the player function. It is very simple. The player P h prime is assigned to each proper subhistory h prime of a terminal history. And fourthly, the preferences, this is simple. Each player prefers h prime to h double prime if and only if she prefers h prime to h double prime in the game gamma. So, in that subgame that we are talking about, which we have defined as gamma h, suppose there are 2 terminal histories h prime and h double prime, then any player will like h prime to h double prime if in the original game the same player prefers h prime to h double prime. So, these are quite intuitive ideas that we are talking about. Basically, what if I have to draw a diagram, it will look like the following. Suppose this is the original game, here the game is starting, and after some point of time, suppose the game reaches here, and this is h. After h has happened, the part of the game that is left after h has happened is called the subgame of the original game. So, that is the idea. So, the player that is why the player set remains the same. In general, this is generalization. The number of players, the players that are there in the subgame can at most be the original player set of the original game. So, we can say that the player set of the subgame is same as the player set of the original game. And terminal histories, as we have just said, that all sorts of terminal histories where h prime is a valid terminal history in the original game, then h prime is a terminal history in this new game that we are defining, which we are calling as a subgame. And thirdly, the player function. For any terminal history h prime, the player function p h, I can apply this player function over this p h prime over every subhistory of this terminal history h prime, and those player functions, that player function will be same as the player function in this new subgame. And finally, the preferences, if there are two terminal histories H prime and H double prime, and if any player likes H prime to H double prime, then he is preferring H prime to H double prime. Again, this is very intuitive. So, this is how the subgame, the idea of subgame is defined. Some notes. First, the subgame following the empty history phi is the entire game itself. This is again very easy to see, and all other subgames are called proper subgames. So, if I take this history to be H, that is this, then we are talking about this entire game itself. The entire game is coming after this subgame, after this history phi. So, the game itself is a subgame of its own, but there are other subgames in a game also, and all those other subgames will be called proper subgame. So, it is like a set and its subsets. The set itself is a subset of its own, that we know, but if I take that subset away, then the subsets that are remaining with me are called proper subsets. So, that is how it is defined. Now, let us take some examples and see how we can find out the subgames from any game. So, let us take this game. Player 1 has two actions. And I am not writing the payoffs of the players because they are not very relevant. Here, how many subgames are there? There are three subgames here. One subgame comes after the empty history itself, which is the entire subgame. That is one subgame. If I take the history C, then this is what is remaining with me, the part of the game that remains with me. So, this part is another subgame, and this is a proper subgame, not unlike the subgame that we have just specified before. And after the history D, we have this other subgame of the original game, which starts with 2 making the first move, and after 2 makes the moves, whatever move it is, the game ends there. So, this game has 3 subgames, but it may happen that these 2 proper subgames are not are subgames of each other. Here, these 2 proper subgames are not subgames of each other, but it may happen that the proper subgames are also subgames of each other. Let us take this game. In fact, I have drawn this before. Let us take this game. How many subgames are there? Now, I claim that here also there are 3 subgames. The first subgame is very easy to see, the game itself, which comes after the history phi. Then there is a subgame which comes after the history C, which is this, and there is a subgame which comes after the non-terminal history CE, which is this. So, here I have 3 subgames. Okay, so I have defined subgame, and the next step is to define what is known as a subgame perfect Nash equilibrium. The idea, let me first try to motivate the idea of a subgame perfect Nash equilibrium, and then I shall try to define it more concretely, more methodically. The idea of subgame perfect Nash equilibrium is this. Is that it's a like the idea of Nash equilibrium in an extensive game. It is also a strategy profile, but the speciality is that this strategy profile should be such that it generates equilibrium in every possible subgame, and in particular also in the subgames which are not included in the terminal history generated by the strategy profile. So, what I exactly mean by this can be illustrated by the following example. This is the familiar entry game once again. And in this game we have seen that outfight was a Nash equilibrium. The question is this a subgame perfect Nash equilibrium? And the answer is no. The reason is that here what is the terminal history which is generated by this strategy profile? It is this out. Right. But this game has a subgame which is not reached by the terminal history, which is this subgame, and this subgame is occurring after the history is in. And what is the action or what is the strategy specified by this equilibrium profile in this subgame? In this subgame, the equilibrium profile is telling us that the incumbent will fight. Okay. And the point is this action of fight is not equilibrium in this particular subgame. So, in this particular subgame, if the incumbent has to move and he has to choose between fight and accommodate, accommodation is better than fighting, because accommodation gives him 1, fighting gives him 0. Therefore, this is not an optimal action, this is not an optimal strategy for the incumbent, player 2. So, that is why we say that this is not a subgame perfect Nash equilibrium, in the sense that this strategy profile is not generating equilibrium in this subgame, following the history in. Likewise, if I have to consider any strategy profile as a possible candidate for subgame perfect Nash equilibrium, I have to look into every possible subgame of that entire game and check whether the strategies of the players in that strategy profile generate equilibrium in those each and every subgame. So, that is what one means by subgame perfect Nash equilibrium. But remember, what I have done so far is just to give an illustration, the vague definition. But now I shall go to more concrete and methodical definition. and here is the definition. So, subgame perfect Nash equilibrium is defined as the following, that for every player I and every history H after which it is player's I's turn to move, this has to be satisfied. Sorry, this let me write it down separately. This subscript is creating a problem. This should be the proper notation. Similarly, this should be OHS. Okay. Now, what we are saying is the following, is that suppose S star is a subgame perfect Nash equilibrium, then S star must satisfy this condition for each player, and for each player and for each non-terminal history H. So, suppose I take any non-terminal history H, and I by applying this player function, I see this is the case, that is, it is now player I's turn to move, then it must be the case that this should happen, which means that if player I takes the action Si star and other players are taking their action S1 star, S2 star, etc., etc., then the game will reach some terminal history after H has happened, right? And that terminal history is indicated by this OHS star. So, this is what is this is saying. Here OHS is the terminal history consisting of H followed by sequences of action generated by S after H. So, if I take any strategy profile S and any non-terminal history H, then OHS giving me that terminal history which is generated by this strategy profile after H has happened, after this non-terminal history H has happened. So, here we are talking about this equilibrium strategy profile S star. I take any non-terminal history, not necessarily on the path of the equilibrium terminal history, which is important. I take any non-terminal history H, and after H has happened, I see now it is I's turn to move. Then it must be the case that I is taking an action Si star which is optimal for him in the following sense, this sense, that if he changes his action, this should be Si. If it changes his action to Si, then his payoff cannot be more. It can either be less or equal, and that is why taking this action Si star is optimal. And this is true for every player I whose turn it is to move after every H, which is just an arbitrary non-terminal history. So, this is the definition, the precise definition of subgame perfect Nash equilibrium. Just to repeat the main point of the definition, we have this S star, which is the profile, equilibrium profile, strategy profile, and I know that every strategy profile generates a terminal history. What is important about this subgame perfect Nash equilibrium is that I do not consider only those subhistories on the path of this particular terminal history generated by S star alone. I take into account every possible non-terminal history H, and I look at the player whose turn it is to move after H has happened, and I look at the terminal history generated by the S star after that H has happened, and I try to see whether the action chosen by I is optimal or not. If it is optimal, then I have got the subgame perfect Nash equilibrium. So that is the basic idea. Now I can apply this idea, as I told you, in case of different games and try to see whether the Nash equilibria that we are talking about are subgame perfect or not. So in this entry game, there were two Nash equilibria. One was in and accommodate, and other was out and fight. Now let us see whether they are Nash whether they are subgame perfect Nash equilibrium or not. I try to give the impression that out fight is not a subgame perfect Nash equilibrium. But before going into that, let us do more systematically and let us look at in and accommodate. Is this a subgame perfect Nash equilibrium? Now I know this in this game there are two subgames. One is after H, one subgame, and after in, this is subgame 1 and this is subgame 2. So there are two histories to be considered after phi and after in. Now one thing which is interesting is that remember that after the phi itself, the subgame that we are considering is the game itself, and in that game, which is just we are looking at the game from the point 0. That subgame itself is the game, and we know that in that game the Nash equilibrium is already in and accommodate. So after phi, I need not check whether in this subgame there is Nash equilibrium or not, because I already know that in the game, the entire game as a whole, in accommodate is a Nash equilibrium. So the only thing I need to check is that after the history in, that is in this subgame, are we getting a Nash equilibrium or not? If we are getting a Nash equilibrium there, then we have got Nash equilibrium in every possible subgame and we are through. So here I can forget about this. So this is the crucial thing that we need to look at. Now here H is in, all right, and what is the equilibrium strategy profile? It is in and accommodate. And how? What is the payoff of the first player, that is the challenger? So let us call this as UCH, the challenger in the subgame following the history in. It is given by in and accommodate, which means he is getting 2. And what is the payoff of the incumbent in equilibrium? It is 1. So this is what they are getting in equilibrium. Point is this optimal? If they deviate, will they get better? Well, if player 1 deviates, okay, if player 1 deviates and changes his strategy to out, so So, I have out now, and the player 2's action strategy remains the same, which is accommodate. Then what does player 1 get? He gets 1, because this is what is happening now. So, it is suboptimal for player 1 to deviate. What about player 2? That is the incumbent. Here he can deviate and he can choose to fight. That is the only deviation that he can do. If he chooses to fight, he gets 0. So, which is less than 1. Therefore, we have the result that in accommodate is a Nash equilibrium, is a subgame perfect Nash equilibrium, because it is generating equilibrium in every possible subgame after every possible history, non-terminal history. What about outfight? So, if I am talking about outfight, this is the thing that I am considering. History, I know if the history is phi, then it is Nash equilibrium. So, that is what we have seen before. But if the history is in, then I have to check whether this is equilibrium or not. So, if the history is in, how much are the players getting? He is staying basically out here, so he is getting 1. The incumbent in equilibrium is getting 2. If he deviates, now if he deviates, how can he deviate? He can choose to come in. So, in and fight, and if he comes in and there is a fight, he will get 0. So, it is not optimal for him to come in. So, that is all right. So, for player the first player, the challenger, it is in fact optimal for him to stay out. But now let us look at the incumbent. Now, he can choose to accommodate, right. Now, here if he accommodates, all right, he will get 1. If H has happened, that is, then he will get 0, right. If H has happened, that is the inaction has taken place, then if he fights, he gets 0, but if he accommodates, all right, then he gets 1. So, for player 2, that is for the incumbent, after H has happened, so after in has happened, if he sticks to his strategy, he gets 0, but if he deviates and accommodates, he gets 1, which is better. For player 1, that is for the challenger, if he sticks to his strategy, which is basically out, he gets 1, and if he chooses to fight, sorry, if he chooses to get in, then he gets 0. So, it is optimal for the challenger to stay out, but it is not optimal for the incumbent to fight, and therefore, out fight is not subgame perfect Nash equilibrium. So, this is one way to show that the idea of subgame perfect Nash equilibrium can be applied to cases where the equilibrium, Nash equilibrium is not robust. The Nash equilibrium is generating outcomes where in subgames which is out of the terminal history generated by the equilibrium strategy profile, the actions of the players are not optimal, and in those cases we can use the idea of subgame perfect Nash equilibrium to rule out those Nash equilibrium. So, let me conclude here itself, and in the next lecture we shall talk about other facets of subgame perfect Nash equilibrium. Thank you. Explain subgame perfect equilibrium. Why is it a more suitable way of looking at steady state in extensive games with perfect information? Subgame perfect equilibrium. Subgame perfect equilibrium, essentially what it means is that it induces equilibrium in each possible subgame of the entire game. Okay. So, technically what we are trying to say is that for every player I and every non-terminal history H, after which I is to make a move, we must have UI, OH, S star, so this is the definition. What we are saying is that subgame perfect in subgame perfect equilibrium, it is not only the case that the game as a whole is in equilibrium, that in the beginning of the game the strategies chosen by players are optimal, but the optimal strategies are there for each and every possible subgame, even in those subgames which subgames are not touched by the equilibrium strategy of each player. So, there might be some subgame which is not reached by S star, small s star, but in those subgames also the strategies of players must be optimal. So, one example will make it more clear. In the extensive game depicted above, which are the subgame perfect equilibrium? We have talked about this game before. Okay, so this was the game, and we have seen that Nash equilibria in this game are 4. These are the 4 Nash equilibria, and we have seen that out of all this Nash equilibria, BFC was a little bit problematic. We said that there was a interpretation of whether this is a steady state. Now, we are now going to show that this is not a subgame perfect Nash equilibrium, not SPE. Why? Let us look at the history AC. Now, after AC has happened, is the strategy of player 1 optimal? That is the question that we are asking. After AC has happened, what we are saying by this strategy profile BFC, what player 1 is getting if he plays according to BFC is 0, but now suppose he deviates and he plays BEC, then he is going to get 1. Therefore, BFC is not subgame perfect equilibrium.